I will present a study called mHealth System Framework for Diagnosing Inflammatory Breast Cancer with Fuzzy Logic. Inflammatory breast cancer, or IBC, is very aggressive and fatal breast cancer. In the United States, IBC is linked with shorter survival rates. It is about 50% 5-year survival, compared to more than 90% 5-year survival of other types of breast cancer. The diagnostic criteria of IBC, as defined by the American Joint Committee on Cancer, AJCC, include erythema, redness, edema, and pedorange over at least a third of the breast, often with no underlying tumor mass. Many IBC patients have symptoms that are different from the restrictive AJCC criteria. They may have no visible redness, less than 1/3 of the breast, or redness but no pedorange or edema. Furthermore, detecting redness, pedorange, and edema is difficult in women with dark skin, such as women from Egypt, many low and middle-income countries, and the United States among African Americans and women of other ethnic backgrounds. In this slide, we see two clinical images of an IBC case, the first two figures, and we can see the pedorange and redness and edema in these two cases. And another figure here, it is a mammogram of an IBC case, and the left breast has IBC. We can see the high density area in the left breast and also the skin thickening. Advances in imaging modalities have improved the diagnosis of IBC. Bilateral mammograms followed by bilateral breast and ultrasound are considered the initial imaging modalities because of their low cost and easy accessibility. Mammograms reveals some of the IBC markers, including skin thickening and increased breast density, calcifications. These are some of the reported characteristics of IBC cases in mammography. Studies reported that about half of the IBC cases had mammographic evidence of nipple inversion. In this figure, we have several images. These are CC view of the mammography images. And the image A and image B are showing IBC cases. Right here, we have IBC present at the left breast, and IBC is present at the right breast. We can see the nipple inversion and skin thickening, and also compare to the other breast, the IBC, the breast with IBC has higher density. We can see the similar characteristics in figure B. Figures C and D are representing non-IBC cancer cases, and figures E and F are showing benign cases. In radiological imaging, IgM may display skin thickening and edema similar to IBC. These characteristics are making the detection or diagnosing IBC more difficult. Developing tools and strategies to improve the diagnosis of IBC are critical to the success of the healthcare infrastructure in lower and middle-income countries and underserved areas in developed countries. Our work presents a currently under development framework describing the various layers of the architecture stages of an M-Health system using mammography, epidemiology, and clinical data. Here in this figure, we can see the computer-aided IBC diagnosis model, and it has 6 stages. The proposed work will have significant clinical and public health implications for early, cost-effective, and improved diagnosis of IBC. It will provide a platform to establish a growing live database of mammography images, epidemiology, and clinical data on IBC for clinicians and nonprofit researchers. Overall, this system may impact the rapid and accurate diagnosis of IBC worldwide. The architecture and the methodology of our M-Health system. The system has 6 stages, and stage 1 is the front-end web system. We can see it right here in the figure. It is stage 1. In this stage, the main end user will be able to use the front end from any device with an internet connection, including smartphones, tablets, laptops, and computers. A secure link will be established with the host server. The main web page will request login credentials from the end user to be able to use the system. If the end user is a new user, they must register first by filling out the new user registration application with their information and credentials. A verification step will ensure that the end user is not a robotic agent. The user will be able to upload the images to be analyzed by the system after signing in. The second stage is the pipeline. Once the end user uploads anonymous, unlabeled images, a unique hash code will be generated for each image, linked with the end user account and added to the processing queue for the next stage. The next stage is the web server. The web server will host the front-end page and process the upcoming images based on the first-in, first-out queue algorithm. On stage 4 is the storage. An encrypted cloud server will host the storage database system and securely store all the uploaded images, which can be retrieved later to be processed by the system. The database will also include the generated decision reports, links to the uploaded images, and analysis reports to the end user accounts. Step 5 or stage 5 is the computer-aided diagnosis system. The computer-aided diagnosis system algorithm in stage 5 is the core of the proposed M-Health system. It is located at the secure backend. This stage will merge bilateral digital mammography images, epidemiology, and clinical data. The feature sets representing each modality will be fused in the future bank, performing a feature reduction selection procedure to avoid overfitting problems in the ML algorithm. Stage 6 is the notification system. The notification system will receive the final decision of the CAD system and will add it to any other required information, such as clinical reports, medical images, to generate a final report. The report will include the diagnostic decision, a chart, and table showing the measured features and differences between the right and left breast, recommended referrals, and a figure showing the case placement for the IBC and non-IBC cancer clusters from the database. In the notification system and in this diagnosis report, we will have, or there will be, two possibilities. One, definitely or almost definitely IBC if the system performance metrics are equal to or greater than 75%. Second possibility is the case needs further investigation if the system performance metrics are below 75%. Here we have the 6 stages I just mentioned and explained their task. And here, this is our overall system. Next is the computer-aided diagnosis model, which is in the stage 5 in our mHealth system. Because of the rarity of IBC, currently there is no open access, public domain, extensive IBC image dataset, and it makes it impossible to design a supervised IBC diagnosis model currently. Our work will develop and implement an ML-based CAD system after the system has a sufficient database. In this early stage of the work, we developed an unsupervised diagnosis system that does not require a large data set. Although unsupervised methods may have lower performance than supervised systems, they are generally considered more robust since their output does not depend on the training data. Fuzzy logic systems are successfully used in classification and diagnosis applications in healthcare. In this work, we designed a fuzzy logic CAD algorithm for the bilateral digital mammography images and obtained preliminary results. The collected mammograms will be processed using image processing techniques to extract distinctive markers of IBC, focusing on skin thickening, high density with undefined borders, and breast thickness. In our algorithm, which is given here in this block diagram, there are several steps. The first step is pre-processing stage. In the pre-processing stage, images are resized by using interpolation. and image contrast is enhanced, and artifacts are removed. Artifacts are the patient's name or the numbers on the mammography images representing the case. And also, in the pre-processing stage, we performed a nipple location, and the nipple location is used as a reference for the next stages. And when we are comparing and analyzing the breast by dividing it into several regions, several parts. Segmentation and feature extraction stages are represented here. Bilateral mammography images are used. This way, both breasts, right and left breasts, are compared. Here in the figure A, the yellow square shows the nipple location, and this nipple location is calculated in the pre-processing stage. Breast density and skin thickening information are calculated. And the skin thickening, here we have right and left breast in this figure here. We can see the figure D has skin thickening and increased breast density. So we can see the skin thickening at the border of the breast right here, and this area here, it is showing skin thickening. And in figure E, also the skin thickening is indicated by the red arrows right here. And the length of the arc here, it is between X and Y. In our calculations, it is representing the arc, and it is arc length. Figures C and F are representing binary images. These are the segmented images and showing the breast density here. We can see the breast in figure D is showing higher density. In this figure, we have the intensity level versus the arc length, and this figure is showing the skin thickening levels around the nipple area for the right breast and the left breast. The red line here, it is representing the left breast, and the gray square is representing the nipple location. We can see the left breast, which has the IBC, has higher skin thickening levels compared to the right breast. Our database has mammogram images, and the image set includes 6 IBC and 8 non-IBC breast cancer cases. The images are acquired by the National Cancer Institute in Cairo, Egypt, and the group got the informed consent, obtained the informed consent and the ground truth in the institution. We designed a type 1 fuzzy logic diagnosis model by using the mean and standard deviation values of the intensity values at the arc and the mean value of the segmented breast density. Here we have the 3D view of the decision hypersurface for the fuzzy logic classifier. The performance of the fuzzy CAD model, including accuracy, sensitivity, specificity, positive and negative predictive values, are presented in the table. The model achieved a promising performance of around 92%, 83%, and 100% accuracy, sensitivity, and specificity respectively. Discussions and conclusions. Our work is a pioneering framework of an mHealth system for diagnosing inflammatory breast cancer, a very aggressive and fatal type of cancer. The goal of the proposed mHealth system is to aid the early diagnosis of IBC to improve survival rates. The proposed mHealth system presents noteworthy innovations. 1. Developing a new, sensitive, and specific CAD algorithm for IBC diagnosis. 2. Enabling clinicians, breast surgeons, and oncologists to rapidly and accurately reach the diagnosis of IBC and initiate the necessary treatment based on differentiating IBC from non-aggressive, slowly growing breast cancers and non-cancer breast diseases. 3. Improving the accuracy of mammography in the diagnosis of IBC, especially in low-resource settings that do not have access or resources for other advanced imaging modalities. 4. Improving the rapid diagnosis of IBC in dark-skinned patients and patients with large breasts in whom the redness, photorange, and edema may be difficult to detect during the clinical examination. 5. Predicting IBC in the breast or recommended more frequent follow-up among patients diagnosed with IBC in this study. IBC patients have a higher risk of cancer than comparably staged non-IBC cancer patients. 6. Establishing a growing IBC database over time. And 7. Improving the diagnosis of IBC in low-income and underserved areas. Our work has some possible limitations, and the limitations and the proposed solutions can be stated as here. 1. Sufficiency of internet connectivity. It is one of the possible limitations. Internet connectivity is required for end users to access the mHealth system. Suppose the end user has a network connection problem. In that case, the front-end interface will send a message to the user about the current status of the data uploading and processing. And the second possible limitation is concurrent request overload. The allowed number of requests will be limited to the server capacity. But if the number of concurrent requests exceeds this limit, the back-end services will expand the computation power and allow the first-in, first-out queue to handle these requests. In addition, proper communication with the front end will be established to show the end user the request current status. Thank you very much.